So today I will talk about, similar to Sophia, I will also talk about the Tc Superconductor. But it's not going to be about the cuprate. It's going to be about a new class of material. That's why I say it's version 2. I will explain. Yeah, so we all know, for last several decades, I think Tc Superconductor just specifically mean one thing, cuprate material. It's a single layer hybrid model, and this is the phase diagram showed by Sophia. So we are familiar with this. From my perspective, I want to view the cuprate as we dope all the multi-insulator because the parent state has 1 electron per site, so it provides a spin 1/2 moment. This phase diagram is very complicated, and in my opinion, this complexity is really related to the spin physics because you have a 1 spin 1/2 moments. Then there are many possibilities, like you can form symmetry breaking orders, and if you don't like symmetry breaking orders, you need to form a spin liquid. Okay, so the physics of cuprate is quite controversial. We have many progresses, but I think in the short time, it's hopeless to reach agreement by all of the people in the field. So the strategy of me is I will not work on cuprate. So my hope is I want to find a new model. In this new model, it's simpler. So maybe we can do something more confidently. So this is my strategy. I want to get rid of these spin moments. So for all the multi-insulator, it's impossible. But then this motivates me to consider even multi-insulator. Basically, I mean at each site, I have 2 electrons. So then I can get rid of the local moments. The simplest case is you just consider a bilayer, like the system like here. So it's like just 2 layer. Each layer is like a cuprate. Okay, but then I add a strong interlayer coupling. So I will not add the bilinear term. I will only add the 4 Fermi interaction. So there is a repulsive V, and the most important term in this talk is this J-perp. So it's a spin-spin coupling between the 2 layers. Okay, so why does this help? Because then you can talk about the multi-insulator with 1 electron per layer. But because of this large J-perp, these spin 1/2 moments between the 2 layers, they just form a spin singlet. It's like a dimer or EPI pair. And then the multi-insulator itself is completely trivial. It's just a product state of this guy. Okay. So no, we don't have local moments. Then our hope is maybe we dope this round singlet phase. Maybe it's easier to get a superconductivity, and maybe it's easier to develop a theory. Okay. So there is one regime I think it's very easy to work out. It's in this regime you don't add a V, you just keep a large J-perp. In this regime, it's like you have an effective attractive interaction from the J-perp. So when you dope holes into this round singlet, you wanted to dope holes at each run. Now you dope 2 holes and each run together, and then this Cooper pair just move. Okay. In the mean-field theory, because this is attractive interaction, you can just do mean-field decoupling of this J-perp. You can get a Cooper pair, and you expect superconductivity. But in this talk, I want to consider more non-trivial cases. So in reality, we always have a repulsive interaction, and this repulsive interaction can cancel the attraction from J-perp. So the question is, if you have a net repulsive interaction, can you still have a pairing? Can you still have a Tc Superconductor? I think that's a more non-trivial questions. So I will show you analysis in 2 regimes, and in these 2 regimes, I believe there is still a possibility of getting a superconductivity, even if the net interaction is repulsive. So in the first regime, I will consider V exactly cancel the J-perp. So the net interaction is like 0, but you still get a pairing from kinetic energy. Okay, and then in the second regime, I will even add a V which is infinite. No, this is a regime you don't expect superconductivity at all. But I will argue, maybe because there is a small to large Fermi surface transition in the normal states, in between there may be a possibility for superconductivity. Okay. So these are theoretical motivations, but there are also experimental motivations. So the first system we look at is the bilayer nucleate. So this diagram shows the experimental data of Tc as a function of the year of the discovery of superconductivity. Most of these materials, they have very low Tc, and they are well described by BCS theory, so we will ignore them. There are only 3 exceptions. The first exception is this cuprate, copper-based materials. The second one may be iron-based. No, I think iron-based is not that interesting, so I will skip it. So the focus of this talk is really this bilayer nucleate. This is a superconductivity which was found just 2 years ago. Our argue, in this material, there is still strongly correlated physics, and it realizes, this bilayer physics we discussed before. So I don't want to get into details of this material, but we can, just give you a very brief introduction of the, chemistry of this bilayer nucleate. So basically, it's a bilayer square lattice. So each layer is just like a couplet. Just the copper atom is replaced by nickel atom. And you can ask, what is the valence of nickel atom? It's close to 3d 8 minus x, which means there are 8 minus x number of electrons in 3d orbitals. If you don't know the notation, it's fine. It just means this nickel set is in a superposition of x equal to 0 and x equal to 1. X equal to 0 just means you have 2 electrons in these 2 orbitals, dx squared minus 1 squared and dz squared. That because of the Hopkins rule, you want to occupy each orbit, and they give you a spin 1/2 moments. And the Hopkins rule also says, these 2 spin moments, they couple to each other, ferromagnetically, so their spin wants to align. Okay, so this is the x equal to 0 state. X equal to 1 means, I dope a hole into this state. So in this system, these 2 orbitals, they are not degenerate. So they are degenerate in the hydrogen atom problem, but our system is constantly 2-dimensional. So there's no rotation symmetry. So there is always a splitting. So that means, you want to dope the hole into the dx squared minus 1 squared. You want to leave dz squared still occupied. Okay, so these are the 2 configurations. And our real system is really the superposition of these 2 configurations. If you look at these 2 configurations, you made an observation that dz squared always have 1 electron. So dz squared is like a Mott insulator. So it provides just like a spin 1/2 moments. So the mobile hole really enters the dx squared minus 1 squared. Okay. So the final model, I think it's like a bilayer counter model. So let me quickly give you an introduction. So let's first look at the 1 layer, top layer. So you have 2 orbitals. So this dz squared just provides spin 1/2 moments. Dx squared minus 1 squared is attenuated electron. They couple together through a JK, which is just -2 the Hopkins coupling. So it's ferromagnetic. Okay, so each layer is really a ferromagnetic contour lattice model, which is well studied, and you don't expect superconductivity. So the new physics is really, this spin 1/2 moments from dz squared in the 2 layers, they are coupled together. Because, you look at the wave function, it's along z direction, so you expect a large hybridization. And this gives us a larger super exchange J-perp. Okay, so the 2 layers are coupled together by a 4 Fermi interaction J-perp. So there in principle should be hopping between dx squared minus 1 squared, but I think it's small, so I ignore it. So for dz squared, because it's in a Mott insulator, so only spin-spin interaction is relevant. So we care only about the dx squared minus 1 squared. So it's like 2 couplet layers, but they couple together. This JK J-perp, you can kind of integrate the dz squared, and you can generate an effective J-perp for the dx squared minus 1 squared. So that's the physics. So we can actually realize this physics of bilayer coupled, couplet layers. Now we can expect, sizable effective J-perp. But the V repulsion may not be that large because they are separated in 2 layers. Okay, so I think this may be a good place to search for Tc superconductivity. So this is one experimental motivation. So there's another experimental motivation, is Tc bilayerography. This was found 7 years ago. So I think this system, this is from the experimental paper. You can see, when you twist the 2 graphite layers by a specific angle called the magic angle, 1.08 degree, you generate a larger super lattice. This lattice constant is at the least scale of 10 nanometers. And the experimenter just says, at this filling, when you have 2 electrons per this super lattice site, there is an insulator, they call it a Mott insulator. And then you dope it, you find a superconductivity. So if you really think in terms of Mott picture, this is an even Mott insulator. Right? So if you really follow the old RVB physics, that there is one obvious scenario is at this super lattice site, you have 2 electrons. These 2 electrons may pair together because of some spin-spin interaction, some interaction like this J-perp. Of course, in this system, we don't have layer, but we have this valley. Valley is like a layer. So there is still, like a J-perp term from electron phonon coupling. It may be more complicated. So here I'll just show you a simple illustration. That the idea is, this Mott insulator, maybe this round singlet. Then you dope it, maybe it moves. So this is actually the most obvious scenario for superconductivity in TPG. But kind of surprisingly, if you search the literature, no one has written this theory. Why is that? The reason is shortly after the experiment, Ashby and Sater, they wrote this paper. They basically said they had a much deeper understanding of the system. There is actually a topological band, so you cannot do the use the multi-insulator picture. So this naive, obvious but naive picture may be wrong. So it was killed even before it generated any output. But after a few years now, I think we realized many people worked on topological band plus interaction, and we realized that even in topological band TPG, there is still a possibility of multi-physics. So that really motivates me to return to the original thought. Right? Let's ignore the band topology. Let's ask, if we can still think in terms of multi-physics, dope multi-physics, what's the most obvious theory you can develop? This is the most obvious theory. And I will present this theory in the second part of my talk. Okay, so this is two outlines. So the first one, which is really my focus, I will focus on this regime. That the attraction from J-perp is exactly cancelled by V. Okay, so I will show you how kinetic energy can drive the Fermi, and I think this is relevant to bilayer nucleate. If I have time, I will focus on this regime. When you have a much larger V, but there is still a possibility of superconductivity, which may be relevant for TPG. Okay, so let's talk about this bilayer nucleate. As I said, we have this effective bilayer model for dx squared minus y squared mobile electron. They coupled together by J-perp. Okay, so if you focus only on dx squared minus y squared orbiter, your model, effective model is like this. The first line is just a two decoupled TG model. It's just a couplet model. Okay. So the new physics is really from the interlayer coupling. That's only 4 Fermi interaction, J-perp and V. The system has a symmetry, U1 cross U1 cross SU2. So it just means that each layer has its own U1 conservation, and they share the same SU2 spin rotation symmetry. Okay. There is also a layer exchange symmetry because I assume the two layers are identical. So the point is, this J-perp actually has, so I assume the parent is from J-perp, but J-perp actually has two independent effects. The first one is it gives you an attraction. So this attraction is exactly the same as density-density interaction. If you do mean feed of J-perp, it's really likely you end the attractive density-density interaction. And this effect can be cancelled by the V term. So actually the net repulsion or interaction is really V minus 1 quarter J-perp. Okay. So if this guy is negative, you expect parity. If this guy is positive, you don't expect parity from mean feed series. Okay, so this effect is kind of fragile. There is another effect is, this J-perp actually penalizes the spin wall configuration of the doublon. So doublon just means I have two electrons together on this run. Okay, so attraction tells you, this doublon has a global lower energy. This second effect just says I don't care about the energy of this doublon. It may be high because of the V term. But in this configuration, I can always focus on the S equal to 0 spin singlet configuration and ignore the spin wall configuration. So this is a purely spin-spin interaction. Okay, this is an effect which is beyond the mean feed series. And what I will going to show you is, even if the first effect is cancelled by V, the second effect can still give you a parity. That's not obvious in mean feed series. So how do we do that? It turns out we can do this in an ideal limit by taking J-perp to be large. It's just the TJ projection because of the Hubbard U. Yeah, it's the familiar TJ projection. Okay, so our approach is, I want to separate this effect. So I will add a V, which exactly cancels J-perp. So effective V is 0. Okay, so I will focus on the second effect. But so far, I only know how to do this in the large J-perp limit, because in this limit, I can do a strong coupling analysis. So the idea is, I view T as a small parameter, as a perturbation. So I ignore the T first. So I just focus on each run, right? Then we have this 4 Fermi interaction, but these are on-site interactions. So I can solve it, exactly. So it turned out, in the low energy, we have, yes. I ignore J parallel as 0. Okay. So I ignore J parallel, yes. I mean, I view T as a perturbation, J parallel should be even smaller. So because of this J-perp in the low energy, I only keep the following 6 states. So I can label them through the quantum number. So the first state is I call it Holon. It just means this run is completely empty. NT is 0. Then the second one I call it signal. It means at each run I have 1 electron in total. Of course, the total spin is 1/2. So you have 4 states because you have 2 spin and 2 layers. And then the third one is I call it doublon. It means I have 2 electrons in this run, and they form a spin singlet because of this large J-perp. So the role of large J-perp is our ignore the S equal to 1 configuration of this doublon. Okay. Then I'll do the degeneracy perturbation theory. I'll just add a T to this restricted Hilbert space. So what you get is just the Hopkins term projected to this Hilbert space. You get another term. It's just the outside energy. It's from a V effective. It just means the Holon and the doublon has lower energy if V effective is negative. So if V effective is negative, you can just focus on Holon and doublon. You get a 2-state problem. As that's just a hardcore Cooper pair problem. It's just a BEC. So in this talk, I will focus on this V effective equal to 0. Net interaction is 0. So then this model is super simple because it only has 1 term. That's the Hopkins term. As you can imagine, the magic really comes from this P, right? P is projects you to this Hilbert space. So the magic comes from the Hilbert space structure. So this electron operator, if you project it to this Hilbert space, it has 2 terms. One is you analyze the doublon and correct the signal, or you analyze a signal and correct the Holon. So there is a parameter relative R. Okay, so this R can be tuned by the macroscopic parameter. Our fix R equal to 1 just for simplicity. So this is a model I'm going to study. Just 1 single term. So I can put it on computer and simulate it. So this is the first thing we did. Just a DMRG simulation of this model. V effective equal to 0, R equal to 1. Only 1 term, T. So there's only 1 unit for the energy. That's the T. So first, DMRG is like a black box machine. You input the Hamiltonian, you can get the ground state. You can calculate the correlation function, but it only works from quasi 1 dimension. So I put the system in a strap. So Ly is actually small. Lx is large. So we tried different Ly. We always found there is a spin gap. There is also a charge 1e gap. So my interpretation is this is a Perry gap. And interestingly, this Perry gap actually has a dome. You dope this is a doublon state. You dope this small insulator, run singlet. The Perry gap actually increases with the doping. And eventually it decreases. So when R equal to 1, there is a particle hole symmetry, which relates this limit and this limit. So around x equal to 0.5, there is a particle hole symmetry. Okay, so that's why you see this symmetric dome. So single electron is gapped, but we also checked the charge 2e is actually gapless. So that means the Cooper pair is gapless. We checked the correlation function, correlation length of 2e over 1e. It increases with border dimension. We also calculate the pair correlation function. In superconductor, it should be a constant, but this is constant 1D, so you only expect the power law. But the power law exponent is small. It can be as small as 0.5. So we think this is a superconductivity. Of course, in 2D, Tc is really decided by phase stiffness. So we also calculated phase stiffness using a periodic boundary condition and a straight flux. It's very complicated, so we only get it for small x. But it seems it also shows a dome. Okay, and the energy scale of the largest value is always at order 1 of T. That's expect, right? Because you only have kinetic energy. So if you have a Tc, Tc must be proportional to T. So I think this is like a kinetic-driven superconductivity. Okay, and it gives you a very large Tc. Tc over T equal to 1 is super large because the interlayer T in solid state material is usually at the order of several thousands Kelvin. Okay, so now this is a numerics. Then you ask, whether we can explain this dome with some simple theory, right? I don't know how to do it exactly, but there is a very simple slave boson mean field you can do. So the problem is we have a restricted Hilbert space. But one way to deal with a restricted Hilbert space is, you imagine this Holon, signal, doublon, they are created by some particles. So Holon is a boson, doublon is a boson, F is a Fermi. There is a constraint, their density is equal to 1 at each filling, at each site. So this gives you a U1 gauge field, but forget the U1 gauge field. In this talk, gauge field is always Higgs or confined. I only talk about the conventional phases. So we do some simple mean field coupling, we just imagine whole long, double long signal, they move independently. Then you do simple mean-field theory, whole long, double long, they just condense. This gives you a variation parameter. The point is, if they condense simultaneously, this is actually a Cooper pair order parameter. So if they condense simultaneously, this gives you a superconductivity. So if you do the calculation, actually you can imagine, in this regime as double dominated, in this regime is whole dominated. So this double condensation must go like this, whole must be like this, and in between there is superconductivity. So that's how we explain the superconductor dome. And this mean field actually matches the DMRG, at least quantitatively. Okay, so it's a very naive calculation, but it seems it works. So you can ask, in this ground state, we have a superconductivity, both whole and double condense. So you can ask, can we have a phase with one of them condensed and the other one is gapped? It turned out, it's possible if you consider the normal state. For example, in this regime, you can consider D is condensed, but H is gapped. It turns out this gives you a small hole pocket. It's a Fermi liquid with a small hole pocket. The picture is almost trivial. X equal to 0 is just a round singlet. It's a vacuum. You dope some hole form a small hole pocket. And there is another limit. You get a different Fermi liquid from X equal to 1. This is the regime which is empty. You dope electron, you get an electron pocket. So if you see the, now you will think these are just two Fermi liquids, but it turns out in this case, these are two different Fermi liquids. You can calculate the Fermi surface volume. One of them is 1 minus X over 2. This is free Fermi result. The other one is minus X over 2 in this second Fermi liquid. So their difference is 1/2 per flavor. No, that's not expected in any mean field theory. So it turns out, so what's the reason? It turned out it's because of this interesting symmetry. So for this symmetry, if you do the Oshikawa-Latinger theorem as Subir mentioned, you will find the Fermi surface volume minus the filling per flavor. Oshikawa told us this is a quantized object, but in this system, it's quantized to be 0 on 1/2 mod 1. So there is a Z2 index for symmetric Fermi liquids. And this Fermi liquid corresponds to the non-interacting fixed point. This second Fermi liquid turned out to correspond to a strongly interacting fixed point. So it's different from the textbook introduction of Fermi liquids. I think this concept is also related to symmetric mass generation because this phase is possible only because of the strong four Fermi interaction. So it's beyond any weak coupling theory, any mean field theory. And we have a theory, how these two Fermi liquids go to superconductivity at a lower temperature. So let me skip this. Yes. One F, yeah. Yeah, its minimum is at pi. Yeah. Yeah, it's just this. Yeah, it's exactly just you form a whole pocket around this pi. Yeah, it's a very simple. Yeah. Yeah, it gets paired. Yeah, so this two regime is really a BCS. Okay, but we have this is like an analog of pseudo gap matter in couplets. Because at X equal to 0, you actually have 2 electrons per site. So in the free Fermi model, you actually expect a large Fermi surface, but actually you have a gap, so it's like a pseudo gap matter. This second, I don't know about the transition. There must be a transition. I don't want to talk about it. Okay, maybe I just want to mention this second Fermi liquid is very similar to the FL star Subir talked about. It's basically FL star by making a spin liquid as a round singlet. So this is the analog. Okay, so this is the first part. So we have this nice theory of superconductivity at the large J-purple limit. Then you expect a super large Tc. We think this is relevant for bilayer nucleate, but for bilayer nucleate, I don't think it's in the this ideal limit. Bilayer nucleate, I believe J-purple is still small. So this is some data from the experiments so far. In this bilayer nucleate, they have many compounds, so they can show how Tc depends on the z-axis lattice constant. So you can find when you compress the bilayer, make the z-axis lattice constant smaller, Tc actually goes up. So this suggests maybe you increase J-perf and the Tc goes up. And so far the change is small, it's just 10%, but the Tc already increased from 40 to 100. But I think there is a large room to improve because my ideal limit may be here. Okay, so the hope is in the future, if the experimentalists can approach this ideal model, this may be a route towards a much higher TC. Right now TC is only 100K. It's kind of small. Okay, so this is the first part. So I want to 5 minutes. Okay, that's enough. So I will briefly talk about the second part. So I will show you another mechanism of getting a superconductivity. But to motivate that, I want to ask this question. So we asked, what is the transition between these two Fermi liquids? The Fermi surface volume dropped by 1/2. Okay, so it's not it's definitely beyond the Landau-Ginzburg, for sure. So one way to study this transition is, you fix the large J-perp and you change the doping. But I want to focus on another regime. Our end super large V repulsive to infinite. The pair is suppressed deep inside these two Fermi liquids. Then at a fixed X, our 2 J-perp. At a large J-perp, it's this model, so we know it's this synchronous Fermi liquid. But at a small J-perp, we still expect a large Fermi surface with area 1 minus X/2. So the question is, when I increase this 4 Fermi interaction, how does this transition happens? So this is a very hard question. So I don't really know the answer, but I will show you a conjecture. There is a superconductor dome in between at the 0 temperature. Okay, and this superconductor is really from because it's close to these 2 different Fermi liquids. So what is the logic? So for this, for this conjecture, it's really a conjecture. I have some intuition, but I don't have unbiased calculation. But there is one question you can ask. Can you describe these 2 Fermi liquids in the same framework? Right? So this second Fermi liquid is beyond any mean field theory. So our still do pattern mean field theory, although there is no topological order. So it turned out, there is a very convenient pattern mean field for this second Fermi liquid is you just do this, double F dagger. This is what I did before. You condense the double F gives you a small hole pocket. But when you go to the finite J-perp, you expect double will also have the spin fluctuation. You have a spin triplet double. So then, it turned out a more convenient way is you split the double to be 2 Fermi, and this 2 Fermi, it's analog of abrasive Fermi, so it represents neutral spinors. Okay. So how do we describe the synchronous Fermi liquid in this language? We just pair up these spinors. So we say the spinor has a pairing gap. Okay, so it's gap out. And then C is really F dagger. It gives us a small pocket here. Okay, so this is the synchronous Fermi liquid phase. It corresponds to this delta spinor pairing. And how do you go to the Fermi liquid? It turned out to go to the Fermi liquid in this framework, you need to introduce this B as F dagger psi. So this B turned out to be just the bound state of electron and the spinor. It's actually the same as the B in Subir's talk. So it's the slave boson. So the hope, my intuition is at a smaller J-perp, this slave boson condensed. At the other limit, delta condensed. Then we get these 2 normal states. Then the transition is if you want a direct transition, you need to fine tuning. So my guess is there is always an intermediate regime. Both order parameter are not 0, and this is the superconductivity. So you can check that. So this superconductivity has 2 sides, from large Fermi surface or small Fermi surface. Of course, at 0 temperature, it's just a crossover. But you can still ask, what is the experimental signature of this superconductivity in these 2 sides? It turned out you can see it from STM. So in the left side, your normal state is just a large Fermi surface. You pair up, you show a gap. But in the other side, the second Fermi liquid is interesting because you have 2 gaps. You first have a spinor pairing plus a small Fermi surface in the normal state. But then you go to the lower T, this B condensed, it gives you a pairing for this small Fermi surface. That's a much smaller pairing scale. So it should give you a second peak. So for this regime, I actually expect 2 gaps. So a larger energy, that's the pseudo gap. A smaller energy, that's the superconductor gap. Okay, so I think this is a nice experimental signature for this synchronous Fermi liquid normal state. It's interesting because some of you may know in magic angle TPG, people actually saw similar behavior this year. So this really motivates me. Maybe in TPG, this is physics. So this is motivates us to develop this theory for TPG. It's exactly this picture at NT equal to 2. I have a round singlet, then I dope it, I get this synchronous Fermi liquid, and then it pairs up. So in TPG, you have a band topology, but it turns out it doesn't matter that much. Okay, so I will skip that. So this is a calculation at a fixed doping. From mean field calculation of this pattern mean field theory. So increase J-perp, you will find this spinor pairing, of course, increases linearly, but the superconductor gap actually increases first and then goes down. So it turns out superconductor actually emerges only when J-perp is finite at the intermediate scale. I can also fix the J-perp and vary the filling. Again, I found in this case the spinor pairing, the pseudo gap always decreases, but the superconductor gap actually first increases and then decreases. And in between, there is a separation, so you expect a pseudo gap. And when you go above Tc, you expect this smaller gap to be destroyed. And this larger gap exists. So the normal state, in my opinion, for TBG is this synchronous Fermi liquid. It's a round singlet plus a small Fermi surface. Okay, so I guess I can just stop. Let me thank my collaborators, postdocs Hanbit, Hui Yang, and Yahui Zhang. So I guess the take-home message of this talk is bilayer model is actually simpler, but it still has some interesting physics. Actually, we expect these 4 phases, they are actually analog of the Couperin phase diagram. But my hope is, in this bilayer model, maybe we can solve them without a controversy, right? We can reach agreement. So that's really my hope. Okay, thank you very much. There are, but the quality is very bad, so you don't really see this. But for the current nucleate, it's definitely not in the synchronous Fermi liquid regime. I think you still see a Fermi liquid. So I think the J-perp is not too large. I think it's still in this regime.
So this large and small gap, the large gap is presumably set by J-perp.
Yeah, it is set by J-perp.
What sets the small gap? Is there a
it's the B. That's the slave Boson condensation. You get it from mean field calculation. It's not that simple, right? It's always compete between, because B, you expect it to be large in Fermi liquid side, but it's small in the second Fermi liquid side. So you always expect this opposite trend. Yeah. Yeah, it's complicated, yeah.
Maybe one last question.
When you talked about the kinetic pairing with J-perp equal to 0, is there a way to explain it by observing that, let's say, effective kinetic energy of doublons and polons, or the 2 allowed states is effectively different because of the projection, or that's the wrong way of looking at things?
I didn't hear the question, so I think for this kinetic pairing, I need to take J-perp to be infinite. If it's finite, I don't know how to do that.
0, that's what I meant. So can you attribute the pairing being due to difference in kinetic energies between 2 allowed states in the Hilbert space, whatever holon and doublon, or do they have exactly the same kinetic energy?
I don't know. I mean, it's just a one-hopping term, right? So, well, this is just my term. I just solved this. I found the ground state is superactivity. Right. So you want to minimize this. Of course, there are actually this term you can actually separate them. Actually, you found that there are different processes. So for example, you can one process is you exchange the signal and the holon, or exchange the signal and the doublon. The other one is you analyze the holon and the doublon and create 2 signals. To get this kinetic pairing, we need this synchronous process. So synchronous process gives us the pairing.
Very good. Let's move on. Thanks.